So in this video, we're going to be reviewing for the final, specifically Chapter 1B. So this is over systems of equation, and there were three methods that we learned for systems of equation. So let's just review that real quick. So the methods we learned for solving systems of equations were graphing, substitution, and elimination. Oop, it looks like I'm running out of room here. Just try to squeeze this in. So like I said before, graphing was the first one where we graph the equations and we see where they intersect, and the intersection is our solution. And then there was elimination, where you stack the equation and then you figure out what opposite, try to get the variables to cancel out by making opposite signs and same coefficients. And then there was substitution. But the most popular one that people tend to use is going to be elimination. So you'll see me using that one a little bit more with the review. So when it comes to elimination, you have to make sure it's in standard form where x and y's are all on one side and the x's and y's line up, and so there's the constants or the coefficients. So when I'm given a problem like this, I'm going to try to eliminate one of the variables, and I can do this by getting the variable's coefficient the same. So perhaps like if I want to cancel out the y's, I would multiply the bottom by a 2, but I would have to multiply everything by 2. So I would choose 2 because I notice this is a negative 2 and the bottom's a positive 1. So I can multiply this with a 2 to make this a positive 2 and cancel it out with the negative 2. So the x minus 2y comes down, so it is a 9. I'm going to distribute the 2 in, so that gives me negative 6x plus 2y, and then I need to multiply this 2 with the 7, so that gives me negative 17. So if I combine my like terms, this cancels. I would have 1 negative 6. If I add that, I get negative 5x, and then this side here is 9 minus 14, which is going to give me negative 5. So if I divide off negative 5 here, this cancels, and x is equal to positive 1 if I divide 5 with negative 5. So my x value is 1. I need to find the y value now. So you can choose either equation. Maybe I'll choose the top equation here. So if I plug in 1 for x, I would have 2y equals 9. So all I did was take this 1, plug it in, and wrote the equation out. And I'm going to try to get the y by itself, because I'm trying to write this as a coordinate for my solution. So in that case, I already have the x value, which is 1. I need to find the y value. So maybe if I subtract the 1 over, I bring down the negative 2y. This is now an 8 on the right side. I'll divide by negative 2, that cancels. And so my y is equal to negative 4. And so my y here is negative 4. My intersections with these two lines, if I were to graph them, they would intersect at positive 1, negative 4. So that is my solution. All right, let's try another one of these. So with this one here, it's kind of nice because both of these are already in standard form, and also the x's already cancel out if I stack them. Notice if I add them together. By the way, elimination, you always add the equations together. The 3x and the negative 3x cancel, so I don't have to really multiply anything in. The negative 4 plus 2y gives me a negative 2y equals negative 1 if I carry down the 1. If I divide by negative 2, that cancels, y comes down, and we would have 1 over 2. And it'd be a positive because there are two negatives here, so it makes a positive 1/2. So I do get a fraction. So I already have my y value. I need my x value. So if I plug this in for y, I would get, let's plug it into the first one here, I get 4 times 1/2. So if I take 1/2 and multiply by 4, you can always put 4 over 1 to make it a fraction. 3x comes down, and 4 times 1 is 4. 1 times 2 in the bottom is a 2. So this is really negative 2 if I divide the 4 and the 2 and reduce. So if I move the 2 over by adding, I now have 3x on this side and a positive 1 on the other side. because negative 1 plus 2 is positive 1. If I divide over 3, my x here equals 1/3, and that is the other part of the solution. So it looks like my coordinate here is at 1/3, 1/2. So that would have been really hard to be able to graph and estimate that this is where they intersect since they're fractions. All right, let's do another problem. This one's a story problem. And so when we're dealing with story problems, we have to make the equation. But first, let's figure out what we're looking for. It says last week at Scale Reptiles store, it received $1,975 for selling 35 reptiles. Iguanas sell for 75 and corn snakes sell for 25. How many corn snakes did Ripley sell? So first off, I know that we made this much as a total and they sold 35 reptiles. I know that each iguana sells for $75 and corn snakes sell for 25, but they are specifically looking for corn snake. So I know that I'm looking for the quantity of snakes that I sold. So perhaps I'll declare my variables first. Now there are two variables here, and I tend to use x's and y's. So I'll make x the iguanas, so number of iguanas, and then I'll make the corn snake my y's. And it doesn't really matter. But the goal is to find y. So I have two variables here, iguanas and snakes. And if I were to make an equation, I know I have 35 reptiles. So I know my first equation could be x plus y, because if I add up all the iguanas and all the snakes, I should get 35 reptiles. So I can use that as my first equation. The second equation here could be something like multiplying the number of iguanas with how much it costs. So $75 times x plus $25 times the number of corn snakes, so y, would give me the total amount that I made at the store. So that would be $1,975. So I multiply how much profit I made with the iguanas and how much profit I made with the corn snakes. Perhaps I would get my total. And so now that I have two equations here, I can go ahead and try to solve for y. So since my goal is to try to get y by itself, maybe I'll cancel out the x's. So if I cancel out x, I would have to multiply by negative 75 to the top, because I notice this is a positive 75. So if I were to do that, my first equation ends up being negative 75x minus 75y equals, let's see, negative 75 times 30. I'm going to type that into my calculator here. So negative 75 times 35 would give me negative 2,625. And then from here, I'm going to bring down my second equation. So 75x plus 25y equals 1,975. So if I combine these two equations, it looks like the x's finally do cancel. Negative 75 plus 25 gives me negative 50y. And then negative 2,625 minus 1, or added with, let me put plus 1,975. If I put this in my calculator here, I get negative 650. Now it looks like I need to divide over negative 50. So that would cancel. My y would come down. And from here, it looks like 650 divided by 50. Now they're both negative, so I know I'm going to get a positive number. This would give me 13, I believe. Let me double check that. So if you have 65 or 650 divided by 50 here, I believe it's 13. Yep, looks like it's 13 here. So if my y is 13, that means I know the number of corn snakes that I sold was 13 snakes. And that's it. Now, if I were asked to find the iguanas, I can go ahead and take 13 and subtract it from 35 and get how many iguanas I sold. In the next problem, we're going to be doing a graphing problem, and it's graphing inequalities. So you might remember this from a while back ago, but anytime we're graphing inequalities, we need to remember that if we have these inequalities we use with a line, we use a solid line. If we have them without a line, we use a dashed line to connect the dots. So just as a reminder. So if I were to graph this, let's go ahead and graph the y-intercept. It looks like it's at, actually, let me make these in two colors. So this is the first equation. This is the second equation. So the first equation is at -1 on the y-axis because it hits it at -1 on the y-intercept. And my slope here looks like it's a 1, so 1 over 1. So I would go up 1 over 1, plot. And then I would just connect the dots using a solid line because there's a line underneath. So there's an equal sign, so I need a solid line. Now it says that this y is greater than this equation. So if y is bigger, you want to shade above the line because these are all the big y's. If you shade below it, these are all the negative y's. So we want to shade above. So I'm going to go ahead and do that here and just shade above. And I'm trying to figure out where does the shading intersect. So right now I know it has to be in this region. Let's check out our second equation. So this equation here has a y-intercept at +1. So I'm going to go to +1 and plot. Now my y-intercept is 1, but my slope is -2, so this is going to be -2 over 1. So instead of going up, I go down 2 over 1 to the right, and I need a dashed line this time because this here has doesn't have a line underneath, so I need a dashed line. So from here, I need to do my shading. It says that the equation is less than this equation. So y is less than this equation. So if y is less, we want to shade below the line because we need negative y values. So if I were to shade below this line, I start to notice that the intersection is right here. So this is where the blue and the pink line intersect. So this is going to be my solution, is this intersection right here. All right, and that's it for this problem here. For 23, it's asking us to know if this triple, this ordered triple, so this pair, and when we have a pair, we have x, y, and z because there are three variables here. So it wants to know if it's a solution. And so if we want to figure out if something's a solution, we have to plug it into all three equations and see if it works out and gives out the number on the right side. So starting with the first equation here, I have 3x, so my x is a 1, my y is a -2, my 3z, my z is a 4. So if I plug this all in, do I actually get 11? Well, let's find out. So 3 times 1 is 3. That would be a -4 plus a 12. So 3 minus 4 is going to give me a -1. -1 plus 12 does give me 11. So this does work out. And if you have to show your work, I would just show this here. So this does give me 11 in the end. So they do end up matching. So this first equation works. Let's try out the second equation. So the second equation, I'm plugging in 1 for x, -2 for y, and z, I'm plugging in a 4. And I'm checking to see if it equals 14. So I would have 2 plus 8 plus 4. I'm multiplying the 2 with the 1 to get the 2. And these two multiply give me a +8. So if I add this up together, 2 plus 8 is 10, plus 4 does give me 14. So the second equation does work as well. So last one here, if I plug in my x, y, and z, so my x is 1, plus my y, which is -2, minus 5 times z, which is 4. And I need to check if it equals -21. So I took this equation, plugged in my x, y, and z, have it written. I'm going to work this part out. So this is going to be 1 minus 2 minus 20, because 5 times 4 is 20. So 1 minus 2 is -1 minus 20 does give me -21. So this works as well. Since all three equations worked, this is a solution. So we can say, yes, it is a solution. And that's it. So this next problem looks like a solving problem, but they already give us the answer choices. We have to figure out which one works. So again, we probably do the same scenario where we choose to plug in our x, y, and z's. And we have to make sure that they work for all three equations. So from here, I would plug in, let's start with our first one here. So I'm going to plug all 1, 2, and 3 in for the first equation. So that would give me, let's see, 1 plus 2 plus 3. Does this equal 5? So this is my first equation here using A. If I plug 1, 2, and 3, that does not give me 5. 1 plus 2 plus 3 is 6. So this definitely doesn't equal. So I can't use A. So that's out. So I'm going to move on to B here. Again, I'm going to start with the first equation. Plug in 6, 0, and negative 1. So 6 plus 0 plus negative 1, does it equal 5? And it does. 6 minus 1 is 5, so this works. So the first one works. Let's try the second one here. So if I plug in my x here, it's 6 minus my y, which is 0, plus my z, which is negative 1, and I need to make sure this equals 15. I already can tell this is not going to equal 15 because negative 2 times 6 is negative 12, minus 1, which is to the side here because 0 would just be nothing. If I subtract this, I get a negative 13. So this does not equal negative 15. So I know B is out. So my next option is C here. And again, I have to start back at equation 1. So plugging in my 6 for x and my 1 for y and negative 2 for z, I need to make sure this equals 5. And I think it does because 6 plus 1 is 7, minus 2 is negative 5. Positive 5. So this does work and give me a 5. So the first one already works. Let's go ahead and check the second one here. So if I plug in 6 for x, that would be negative 2 times 6 minus my y, which is 1, plus my z, which is negative 2. And this needs to equal 15. And so negative 2 times 6 is negative 12, minus 2 minus 2. So negative 2 minus 1 is negative 13, minus 2 does give me negative 15. So this does end up giving me negative 15. So the second equation works. So this might be it. So for the third equation here, we would be plugging in our 6 minus our 2y, which is a 1, minus our negative 2 for z, and this needs to equal 6. So if I work this out to the side here, since I've ran out of room, I would get 6 minus 2, because 2 times 1 is just going to end up being negative 2. 2 negatives here would make a positive 2. And I think this definitely will equal 6 because negative 2 plus positive 2 would cancel, so you'd be left with 6. So this definitely works out. It looks like C is finally our winner here. That works. All right, so that's it for that problem there. The rest of the problems are all about types of solutions. So for 25 here, it says explain the 3 different types of solutions that you can have when solving a systems of equations. So we've mentioned this before. There is the one solution, there is no solution, and there's infinitely many solutions. So in our case, if you make a graph for one solution, that's your typical type of lines. If you have 2 lines and they happen to cross, they're going to usually cross at one place, and so this is why there's only one intersection, so there's one solution. Whereas the one that has no solution is where when you have 2 lines that happen to be parallel, so they never intersect, so this is only happening if you have parallel lines and they never intersect, so there are no solutions to look at. The last one here is if you have a graph, and let's say you have graph 2 lines and they happen to be on top of each other because they're the same lines. So you've actually just graphed one line. So if they happen to be 2 lines that are the exact identical, they're going to be on top of each other, so they intersect everywhere because they are the exact same lines. All right, and then 26 here talks about, so these we're explaining it graphically. Can you explain it algebraically, where you talk about the types of solution? They want to specifically know about no solution and infinitely many solutions, but I'm going to refer to all 3 of them. So if you have one solution, this is nice. This is kind of like the problems we had before where we had to do elimination. You actually find an x value. So you find an x value and you find a y value. So you solve out the equation and you actually find numbers for x's and y's. No solution is where everything cancels and then one side is equal to 0 and then the other side is equal to some random number. But basically your equal signs don't match up. So they're not the same numbers, so this is a no solution. Infinitely many solution is when you're solving it out and both sides end up canceling, so you get 0 on both sides, so you basically have something that's infinitely many solutions. And that's basically it for this chapter.